couple of announcements now that we are recording. First, office hours this week. I know that Fridays will be changed because normally I'm on Birmingham campus 7:45 to 11:45 on Friday, and this Friday not, because I have a regular treatment this Friday. I had my first treatment on the new drug on Friday, small thing, 300 milligrams, and everything went well.
Were you there for 7 hours?
I was there for very close to 7 hours.
Oh my God.
Because about started around 7:30ish, and or somewhere around 11:30ish, I started getting very uncomfortable, hot and itchy and stuff like this, and I started looking, and I had big blotches of red, reaction to the stuff. And I told the nurse, and she, oh yeah, you're having a reaction. And so what she did was cut off the drug for a while and give me another dose of Benadryl. And so that made me sleepier. And she waited till the symptoms pretty much had died down and then turned it back on again. She had gotten it up to full speed, and she cut it back to half speed. So that took the rest of the afternoon. Now that was for 300 milligrams. I've got 1,000 milligrams coming up this time, 3 times the amount. So it's going to be interesting. But they said usually if you have a reaction it's the first time, and sometimes you don't anymore. So your body just sort of gets used to it. So, but I know I'll be out all day Friday, okay, because I have to actually be in at 6:30 for labs and 7:30 for the treatment, and they figure another 7 hours. So no way I'm coming back to campus Friday. Now, here's sort of the bad news. It doesn't directly influence this class, but it may office hours-wise. Next Tuesday, not tomorrow, but next Tuesday, voting day, by the way, I have an appointment with my hematologist, and he only sees patients on Tuesday mornings. So I know I'm going to miss all of one class, probably all of 2 classes, and possibly most or all of 3 classes. So I've got all those to make up sometime. I'd like to make them up for all 3 classes. So that means, since my office hours now, basically the only really free office hours I have right now are Tuesday, Thursday, 12:15 to 3:15. That's it. I usually have lunch somewhere in there. So if I make up one class each of those, that would be 3 days. And I could either start it this Thursday. I could start it maybe tomorrow, but I'm guessing Thursday, Tuesday, and Thursday probably will do. Now, the other option for me would be Monday, Wednesday afternoon, because I get off technically at 2 o'clock, that I may, right after this class is over with, do a class right after that. But I figured they'll probably prefer to have it on days when the class meets. So we'll figure that out probably by Wednesday. Hopefully I'll know. So there are some office hour changes coming. What's that? Yeah. At least for a while. Was there something you needed? Or? Oh, okay. Oh, yeah. I'll be here definitely till, I'm almost always here till 4:45, sometimes 5:15. Today, I think I need, if my memory's right, I need to run by Sam's on the way home, so I might leave a little before 4:45, but technically I'm supposed to leave at 2. I'm not leaving at 2. It'll be at least, no earlier than 3 or 4 probably. Yeah, I'll probably. What's that? Okay, yeah. I'll be here until I see you probably. But even if not, you can slide it under my door. And if it's there, yeah. And you got to, finished? Okay. I guess enough of that. So, any questions on anything we've done so far? Okay, we're in Chapter 13. That's Calculus of Vector-Valued Functions. And 13.4 is curvature, and that's where we were last time. We did this slide before. Now, frankly, to me that looks a little fuzzy. Is it to you or?
I'm gonna blow it up.
Yeah, let me blow it up and see if it's still fuzzy there. I'm not doing this one. We did this last time. Is it okay?
Seems all right.
Okay. All right. So we're going to be talking about the normal vector. We got right up to it, but didn't quite get to it. Now, it's not that other vectors are abnormal. This is just a vector that means perpendicular to the curve. That kind of normal. Okay? And here is the, sorry. If you recall, we had noted before, let me get my pen activated, okay, that the unit tangent vector's first derivative, which by the way is no longer a unit vector, okay, and the unit tangent vector itself, so therefore I guess for the first derivative are probably, just for my own purposes, probably shouldn't use that notation anymore. Even though the unit tangent vector is a unit vector, its derivative is not. So this and t of t, that is a unit tangent vector. These are orthogonal to each other. Okay? Unit tangent vector, of course, tangent to a curve, whatever curve you're dealing with, is tangent to it. Its derivative is going to then be perpendicular to that unit tangent vector. Okay. Well, a vector perpendicular to a tangent vector is then by definition perpendicular to the curve at that point. So therefore, it would be in the direction of the normal vector. Now, the unit vector in the direction of this first derivative of the unit tangent vector, if it's non-zero, then it's called a normal vector. The unit vector that's perpendicular or to that is called the unit normal vector, and it's denoted by n of t. Okay? Now, or simply just n. And here is, then, based on what we just said, the unit normal vector, n of t, is in the direction of the first derivative of the unit tangent vector. Remember, this is not a unit vector anymore. The tangent vector was, but the derivative is not. So divide by its magnitude to get the vector in the direction of that normal vector and make it a unit vector by dividing by its magnitude. That's how you get a normal vector. If you know the vector direction, then divide by that. Now, this pair then of unit tangent vector, unit normal vector, unit vector, of orthogonal unit vectors play a critical role in understanding the given space curve. Now, if you recall something, got to get out of that, about this now, the first derivative of the unit tangent vector, remember just a few pages back, page 713, that equation 2 right at the side of the page, that magnitude of the unit tangent vector, magnitude of the first derivative of the unit tangent vector, is kappa times the velocity vector. So since this thing is kappa, the curvature, okay, which is typically a function of t, times the velocity vector, which is certainly a function of t. No, speed, not velocity. That's not a vector. It's a scalar quantity. Then we can rewrite this to be the unit tangent vector, and the first derivative of the unit tangent vector is equal to kappa of t times v of t times the unit normal vector. Whoops, unit normal vector. Okay. And that's this equation. That's how they derive that and get it. Written maybe a little bit nicer than I did. Okay? Now, they use this term, I think, a little loosely, intuitively. Okay? I'm not sure how intuitive this is, but mathematicians love to use that. Intuitively, n, the unit normal vector, points in the direction in which the curve is turning. Because if you think about a tangent vector like this, the curve could be over here or over here, but the tangent vector would be here. Well, the unit normal vector is always in the direction that the curve is turning. Whereas it's the first derivative of it, you know, who can say whether that should be pointing inward or pointing outward, okay? But it just happens to be always pointing inward, okay?
So it was like a circle that would be pointing towards the center.
Toward the center, absolutely. In fact, exactly toward the center, yeah, exactly. Okay. And supposedly there is a curve drawing here. Yeah, okay. Okay. So for a plane curve, this is in the plane, not in space, but in the plane. If this is your curve, the green curve here, the unit tangent vector would be in this direction. I did a lot of work over the weekend, and I'm sore, moving my arms with aches, you know.
Arm waving is down.
Yes. Oh, painful. It feels like I've had 3 flu shots in it. You know, it's that painful, you know. Okay. For a plane curve, the unit normal vector points in the direction of the bending. It would not point out this way. Whereas you might say, which way is the first derivative of this pointing? I mean, the perpendicular to this pointing, it could be pointing here or here. Unit normal vector always points that way. Now, here's sort of rationale of why. Because think of that, the first derivative of this vector would be, how is that vector changing with a little bit of time? Well, if it's here, then a little bit later it's here, its change is going to be in that direction, not that way. It's going to change with the curvature, because the next vector here, point there, is going to point there in the same direction. But as you can see from that, the first derivative of this is probably going to be a very small vector. Then you have to expand it to make it a unit vector. If this was a really sharp curvature, its first derivative would be quite long, and you'd have to shrink it to make it a unit vector. That's why the first derivative of this is not a unit vector, even though the unit tangent vector is, of course, a unit tangent vector. So it always does point in the direction of the bending. Okay. I don't know if that arm waving helped or not, but it hurt. No, I'm sorry. All right. All right. What's that? Example 5. Find the unit normal vector at t equal pi fourths for the helix, and this is a 3-dimensional shape, now not a plane curve like we just had, but 3-dimensional. R of t is equal to cosine t, sine t, t. Our good old favorite helix. Okay? Now what we're asked to find is find the unit normal vector at t equal pi fourths. Where would you begin? Yes, take a derivative of your displacement vector, and that gives you your basically velocity vector. Okay? And what would that be? Negative sine t cosine t, 1. Okay. Now that gives you the velocity vector, which is always tangent to the curve, right? So how could you get from that, what would you get next? What would you go for next?
Magnitude.
Yeah.
R prime of t.
Okay, yeah. And why, okay, let's get the magnitude of r prime of t. While we're here, r prime of t, magnitude would then be the square root of negative sine t in quantity squared plus cosine t quantity squared plus 1 squared, right? Which would be sine squared t plus cosine squared t plus 1, which would be, second, square root of 2, because sine squared plus cosine squared is always 1, plus 1 is 2, square root of 2. So that's the magnitude of the velocity vector, or the first derivative of the displacement vector. Why did we get that? Why did you want that? And what would that give you? No, the unit tangent vector. Remember, the velocity vector is tangent to the curve. Okay, so that's what we went for next, the unit tangent vector. So, unit tangent vector t is the velocity vector, well, like I said it, it's the velocity vector,
Still R prime.
r prime of t. It is the velocity vector, but it's r prime of t divided by the magnitude of r prime of t. And that gives you the unit tangent vector. So in this case, that would be, yeah, negative sine t over root 2, comma, cosine t over root 2, comma, 1 over root 2, or you could call it square root of 2 over 2. Whatever you want to call that. I mean, over root 2 is fine in the first two, why not in this last one too? Whatever you, that value. Okay, now, that gives you the magnitude of the unit tangent vector. What's the next thing you've got to do? Yes, because you need the derivative of the unit tangent vector. So we'll do that next. And just so you won't think it's a unit vector, I'll put the vector sign. What would that be? And you can pull out the 1 over root 2. I should have anyway. But anyway, what would that give you? Negative cosine t. Negative sine t. It's a constant. 0. Okay. Now that tells you a little something, not much, but a little something, that the change, okay, your unit tangent vector, which is in the same direction as the velocity vector here, is in free space too. But its derivative is only in xy space. I mean, its z component is 0, which means that's level, okay, parallel to the xy plane, okay? This picture doesn't really show that, I don't think, well, okay, but it is indeed parallel to the xy axis. Maybe that's what this is supposed to be representing, that is indeed, this is an xy plane, and that's parallel to that plane. That's what it should be showing, okay, whether you picked up on it or not. Okay, why did we do that? What do we do next? Yeah, now we need the magnitude of that one. And what is the magnitude of this one? The square root of? I would say so because that's part of it, and you're squaring it, so that would be okay, negative cosine t over root 2 squared plus a negative sine t over root 2 squared. Done, right? There's no z component. So what is that? Yuck. Yes. Plus sine squared t over 2, which is? Okay, the numerator would be 1. Okay, square root of 1/2. So that would be another 1 over root 2. So the square root of 1/2. I'll write it that way. Okay. Now we can do the unit normal vector. The unit normal vector as a function of t is indeed that unit tangent vector, which is 1 over root 2 times this. Minus cosine t minus sine t0 over another square root of root 2. 1 over square root of root 2. Okay? Which, of course, now they go out. And does this make sense? Is minus cosine t minus sine t 0. What's its magnitude? 1. Exactly. So that is a unit vector. That is your unit normal vector. Okay? At any time t. What the problem asked for was at t equal pi fourths. So the unit normal vector at t equal pi fourths would be, almost feels like you're running in circles, doesn't it? Yeah, especially at pi fourths, that would be yes, negative the square root of 2 over 2, comma, negative the square root of 2 over 2, comma, 0. Which, by the way, root 2 over 2 is 1 over root 2, so you got another 1 over root 2 in there everywhere. But yeah, that's it exactly. Okay? And that is, by the way, a unit vector, because if you did the square root of this squared, that would be 1/2 plus 1/2 plus 0 would be 1 square root of 1. Yeah, that does work out exactly. Okay. And this is the figure that shows that as well. And it is a unit normal vector pointing to the z-axis, pointing right toward the z-axis. This looks like it's touching it. Yeah, indeed it is. Because that, the level curve, or the, what do we call that? We had a name for it. Maps here, that's one name for it. When you look at a curve and just look at it.
On one plane.
Yeah, on one
It'd
plane.
be a unit circle.
Yeah, and that would be the unit circle, so therefore its radius would be exactly 1, so that would be pointing right from here to exactly touching the z-axis. Exactly. So that is drawn correctly. Okay. So it says, note that at every point on the helix, the normal vector is a horizontal vector that points directly back at the z-axis. It reflects the fact that the curve is always turning back toward the z-axis, and its trace, that's what you call it, its horizontal trace is a unit circle. Yeah. So therefore it's normal vector would be the radius of that curve. Now, for those of you who have the older text, do any of you have that? Is your next thing the Frenet frame? I don't remember this being in the older text. After example 5, what's the next thing you have? The what? Okay. And that's, well, it's basically doing the same thing. They just give it a different name. Okay. Well, not quite. Okay. Figure 14 is the osculating circle in our text, and that's probably the, well, we'll get there. So there is something else put in that's not in the old book, and this is the first time I've run into this, the Frenet frame. I believe I'm pronouncing that right. Given a point on a curve corresponding to a parameter value t, we have now introduced two unit vectors at that point. The unit tangent vector, which of course is tangent to the curve at that point, and then the unit normal vector, which is perpendicular to the curve at that point, pointing inward toward the curve. Okay? The unit tangent vector points in the direction of motion, and the unit normal vector points in the direction of the turning of the motion. Okay? Okay. There is a third vector that is related to the first two, and that together with those two provides a frame of reference at that point, and this is called the binormal vector. And I'm not sure why they chose that term, but that vector is typically given the symbol B. All right, Victor's here. Oh, and Ashley's here. Keep them coming. Okay. All right. So right now we're up to 5 out of 9, so we're only missing 4. That would be Tony, Javon, and Jonathan. Are we down to? Oh, I guess we're down to 8 now. No, that's right. We're got 3 out of 5 missing. 5 out of 8 missing. We must be down to 8 students today. 1, 2, 3, 4. No?
We have 6 people here.
Oh, we have 6 here. No wonder I can't count. That's it. Okay. So we are missing 3. Tony, Jonathan, and Javon. That's it. Okay. Make sure I've got 6 people marked. Yeah. My Cal 2 and Cal 3 go together so much I thought one of those was okay. Yeah, got 6 here. Good deal. All right. Now, so part of what does your older edition refer to the binormal vector at all here? Okay. It's going to show up later, but they put it in here now. But I did not remember the Frenet frame, which is the frame of reference you get by these 3 vectors. Okay, we're going to come back to this figure in just a moment. No, I'm sorry. This is, in the old book, this is figure 12. In the newer edition, this is figure 13. The one that's missing is the one with the binormal vector. Okay? And let me see if I can draw that for you. Okay. My 3-dimensional drawing skills are next to non-existent. Okay? So bear with me. If this is, say, some curve, certainly at this point here, the unit tangent vector would be like this. So there would be the unit tangent vector. Okay, the unit normal vector would be something like this. I don't know, probably don't have the size right. That would be the unit normal vector. Okay, always inside part of the curve, which way it's turning. Now, the binormal vector would be right-hand rule, tangent cross normal, so that would be pointing in this case, somewhat upward, and let's just say it's like this, and there would be the unit binormal vector. Okay. Yeah, and these two at right angles to each other, these two are right angles to each other, and these two are right angles to each other. I can't get all my right angles in there. In fact, they don't show the two of the three in the text. Okay, they don't show unit tangent, unit normal, because they just assume you know that. Okay, so as I've just indicated here, the binormal vector, why in the world? Okay, the binormal vector, and that's a unit vector as well as a function of t, is the unit tangent vector as a function of t, crossed with the unit normal vector as a function of t. Okay, that's your definition. Okay, the fact that B is a unit vector is verified in exercise 83. Since T and N are already perpendicular to one another, and since by definition of the cross product, the result of the cross product is perpendicular to both of the other two, then this does form a perpendicular system. And these three vectors, and we usually refer to them in this order, T, N, and B. In that order, that makes a frame of reference, and they call that the Frenet frame. To me, Frenet frame of reference, they just leave off the F reference. After the French geometer Jean Frenet, okay, and he lived, by the way, 1816 to 1900. And if you think about what was happening in that time, 1816 was within probably, I don't know exactly the dates of the French Revolution, but it was no more than 25 years after that. So he was born shortly after the French Revolution and lived in that time frame. Can't say a lot about what was happening in that time frame for France, but at least for the U.S., we had our war between the states then. France was not overly involved with that. So I think this is usually considered to be sort of a peaceful time for Europe. Seemed to have been, but France and England were always fiddling with each other. But anyway, it was a time of probably pretty good advances in science when they weren't worried about going to war and stuff like that. Yeah. Question?
You mentioned Frenet formula, but it doesn't talk about it like you just did, but it gives problems and everything.
Right. Okay. Oh, it gives them in the problem set. Yeah. That's how some of these authors do it, and it sort of irritates me. So, by the way, the reason I went into all that, Jean Frenet would be a good paper topic, okay? Or how he came up with this frame of reference, or why he came up with that frame of reference, and then maybe some of the applications for that. So you could get 2 or 3, maybe even 4 different paper topics out of that if you're interested. And by the way, our little side note here says the Frenet frame, also known as the Frenet-Surette frame, or the TNB frame, tangent, normal, binormal, okay, depends only on the intrinsic properties of the space curve and needs no outside reference coordinate system. As such, it is very useful in analyzing the path of a spacecraft, satellite, asteroid, or anything such as that. You don't need a predetermined frame of reference. Just where it is and where it's going, that gives you the Frenet frame. Okay, let's go to example 6. It says, continue example 5 to find a formula for the binormal vector for a point on the helix r of t equal cosine t. Okay. Yuck, I erased it all. Sorry. Let me erase this stuff I've got here, though I probably do need some of it, but hopefully you remember it. Let's jot down what we had for our unit tangent vector. Okay, let me back off here a minute. All right, let's go back to the helix. R of t is equal to cosine t, sine t, t. Okay. You tell me what we got as the unit tangent vector for that curve, that helix.
You want it with the, you already got it.
Yeah.
Cosine t and 1.
Okay. Minus sine t, cosine t 1, right?
Right.
With a 1 over root 2 in front, right? Okay. What was our unit normal vector? Whoops. I could write it like that, but I like to write it with the caret on top. Okay. And remember that was minus cosine t minus sine t, 0. So you tell me what the unit normal vector, binormal vector would be then.
You got to
Cross those two. Very good. So you're going to have 1 over root 2, right? Now, do you remember how to do the cross product? And remember, the order matters on this cross product. I, J, K minus sine t, cosine t, 1 minus cosine t minus sine t, 0. Second? Okay.
Cosine t times 0, 0, minus negative sine t, 70 plus sine t.
Okay. So this will be a sine t. Is that what you're telling me?
Yes.
Okay. I don't know if you like to do it this way. I know one doesn't, but I do. I minus sine t minus cosine t and j cosine t minus sine t. Okay. Let's do j, and that would be okay. Right.
Oh, you said j.
J, yeah.
Okay,
So
that'd be 0 minus, it'd be a positive cosine.
okay, how do you get that?
Negative sine t times 0, which is 0.
Okay, why do you start that way?
I'm doing it the normal way.
Okay. Okay, but if you did that, then it's a minus position. You start with that then. And then minus would be, okay. So going the normal way, if it's called that way, it's a minus position, right? Plus minus. So that would be 0 plus cosine
Plus
t
cosine t, but it'd be a minus.
minus, so it would be a minus. Right. And if you like keeping up with all those minus signs, that's a perfectly good way to do it. Whereas if you do it extended out, all you have to do is just like normal, minus cosine t.
Just like,
Either way works. Either way works. That's why you're allowed to do them either way. All right, so that's your
right, and then k,
K would be,
is that a negative sign? Yeah.
yeah,
So that'd be sine t squared.
right?
Sine squared t minus, or be plus cosine squared t, which is 1. Right?
Yes, so that would be 1. Now the question is that indeed a unit vector? Yes, it is, just like that this one was. See, it has the same components, just signs changed, but so you have to have a component of square root of 2 out front, because otherwise you do the square root of sine squared t plus cosine square z plus 1. That'd be 1 plus 1 is 2. So you need to divide by square root of 2. Sure enough, that's it. All right. So there is your b of t. They write it out sine t over root 2i, which is what we have, sine t over root 2i minus cosine t over root 2j plus 1 over root 2k. They didn't write it in component notation, or they did, but they wrote it in IJK notation, which is perfectly fine. Now, actually, they wrote the plus here and the minus there. That's still the same. Nothing changed. Okay. Good deal. Any questions on that? Now, here is where the old book picks up now. We conclude by describing another interpretation of curvature in terms of the osculating or best fitting circle. And let's suppose that P is a point on a plane curve C, which we have here. I'm going to take this off since we're through with binormal for right now. Okay. So here we have a plane curve, xy plane. Okay. The blue curve is the curve in question. This one here, this blue curve here. Okay. It's just some old curve in the xy plane. Okay. Now, suppose P is some point on that curve C. The blue curve is curve C, and there's our point P. Now here is the R that goes from the origin to point to that P. So this R vector here, this is vector R, and we'll call that T0 that gets you right there to P. Okay. So that's our setup. Now, suppose P is a point on the plane curve C where the curvature KP is non-zero. Okay, now what does that basically mean to you? What would be a curvature of 0? Straight line, exactly, okay? So this is not a straight line. The curve is curving there. Now, it happens to be this point P they chose is not too far from being. Back here would be even closer to being a curvature of 0, because you see between here and there.
It's almost like in line with your tangent line.
Exactly, exactly. And what I was going to say with that was, this would be, since we're talking about a plane curve here, this would basically be a point of inflection, where it changes from this to that. Right there, the tangent, yeah, that would be awfully close. I think would be exactly. But this is just past. See here, it's concave down, here it's concave up. You're on the concave up side of it. Right there at the point of inflection, wherever that would be, I'm just guessing, then there you probably would have a 0 curvature. Down here you have a curvature up here you have a curvature down. So you do have a non-zero thing. But you could run into, even on a continuous curve, you could have a place, and you would. Conceivably, on the three-dimensional curve, it might be a little harder to do, but you could have a place where the curvature was 0. In other words, temporarily, right at that very instant, it mimics a straight line. But this is not. Okay. Okay. I lost where I was. Okay. Where the curvature KP is non-zero. I'm sorry, I keep saying KP. Kappa sub P. That's a kappa, not a K. The osculating circle, denoted by OSC, okay, O subscript, SC subscript again, P, okay, you got two different subscripts in there, is the circle of radius R equal 1 over kappa sub p, that curvature, through P, whose center Q lies in the direction of the unit normal vector. In other words, the center Q is determined by, and we'll get to that in just a second. Here is the situation now. Here is a curve, the blue curve, they called it C. We pick some place that doesn't have a zero curvature, okay, and over here it's curving upward, so that is a non-zero curvature. Now, the unit normal vector there is pointing toward some imaginary circle whose center is at Q. And that imaginary circle would have a radius, this R right here, and of course when I go to write it, it's going to shrink, so I got to shrink it to get it there. This R right here is this 1 over your kappa, or curvature, at the point P. Okay? So, if this is a big old circle here, that is a small k, kappa, approaching 0, okay? And 1 over that would be a very large radius. So, at that place where your curvature would be 0, you have an infinite radius. That would be a straight line. Right? Said that, okay? So, the center Q of the osculating circle at P lies at a distance r, which is 1 over kappa at P, from P, that distance from P, in the normal direction. Okay? Obviously, the osculating circle, since the normal line here, the circle that best fits the curve right there would be the circle whose radius is 1 over kappa and whose center is in the direction of the normal vector. How far in that direction? The radius, which is 1 over kappa P. Now, that describes what we've got here. Now, it says here, in other words, okay, the center Q, that center Q right there, is determined by this OQ, that line, the dotted line you see there, OQ, is equal to R of T0, which gets you to P, plus Rn, that gets you 1 over kappa P, times, in the unit normal direction, so that's time n. The sum of those together gives you that circle, the center location Q, as okay. Among all the circles tangent to C at P, the osculating circle, by the way, let me write it down, OSC at P. So it's a double subscript. O subscript SP subscript again P. Okay? Strange but true. Okay? That osculating best fits the curve, and exercise 79 will follow up on that. We refer to R, that capital R, 1 over kappa P, okay, as the radius of curvature at the point P, and the center Q of the osculating circle OSCP is called the center of curvature at P. So let's do example 7. Okay, I think example 7, yeah. Oh, sorry. Didn't realize I had this as a... Example 9, I didn't notice it was a numbered example, or I would have known this was on the slide set. This is OQ. It's from the origin, wherever that is, to the point Q, which is the center of the osculating circle, is R of T, which is the vector that gets you from the center to the point P, plus 1 over kappa, which is your radius times the normal vector. Normal vector points you to the center, and 1 over kappa b gets you exactly that distance, because the normal vector is magnitude 1. So you're scaling that up to there. So then 0 to that q would be exactly this sum of those two vectors. Okay? Now, here's example 7. I guess it is. Is it example 7 in the old text too? Seems like it is, but okay. Parameterize the osculating circle to y is equal to x squared at x equal 1/2. Okay. Now that this figure does not directly relate to this problem. I mean, the curve is the same, the parabola is the same, but this isn't the osculating circle. None of these are the osculating circle they're asking about, because these are all from point P, which is the origin, not P, which is equal to x equal 1/2.
Which is a little bit to the right.
Yeah, it'll be a little to the right, and you'll have another oscillating circle here, but not centered down here over on the side. Okay. So I'm not sure why they have this figure with this problem, but we're okay. So parameterize the osculating circle to, let me just write it in. Well, of course, when I go to write it in, it's going to shrink. Nope. Okay. Parameterize the osculating circle to the circle. This is y. Why is my pen not activating? Okay, now maybe it has. Y is equal to x squared. Okay, there's your curve. And we want it at x equal 1/2, which isn't listed here. None of those circles are there. Okay, so we need a parameterization for the osculating circle, so we need a parameterization for the whole parabola. And what would that be? R of t would be what? What would be a good parameterization for that parabola? Well, and this is xy plane, so you only need two components. What would be a good thing for x?
You need an x and a 1, right?
No, you need that in terms of t's.
So
T,
squared.
t squared. That is an excellent parameterization for that curve. Okay? Now, except they're not using t. This, to me, gets to be rather bizarre. They're using x as the parameter too. So, r of x, huh? Yeah, let's just use t. It seems like to me they've gone to great extents not to do this before, and now all of a sudden they're allowing themselves to do it. So I prefer to go this route. Okay? Okay. So there's our parameterization. Okay? Now, what have we got to do to find the osculating circle? Parameterize that osculating circle. Say again? I can't hear. Find the radius. Sounds good. How are we going to go about doing that? Okay. Oh, I see. Step 1 says finding the radius. Clever. Okay. All right. We need to compute the curvature, because 1 over the curvature, kappa. Okay? So how do we get kappa? By the way, if you haven't had it before. The curvature of a graph in a plane, if you turn back one flip of a page, you get kappa as a function of x, which is exactly what they're using, and there it is. So, okay, and yeah, so here your y prime was, going back to x's here, y prime was 2x, and y double prime is 2, okay? And the absolute value of 2 is 2. So your kappa, now kappa is a scalar quantity, and we're going to do it in terms of x now. Well, we can do it in terms of t, since we've done t. That would be 2 over 1 plus, what was your f prime? 2x, so that would be 2x, and you square that. Now remember that square there, I like to put after the prime. It's the first derivative squared, don't think that's x squared, it's our first derivative squared. Okay, and then you're going to take the 3/2 power of that thing. Okay, so this again will be x in. So this will be 2 over 1 plus 4x squared to the 3/2 power. Okay, that's kappa as a function of x. So that's your kappa. You want, let's get kappa at x equal 1/2. And that would be 2 over 1 plus 4 times, okay, and 1 plus 1 is 2. High math today, isn't it? So that would be 2 over, okay, it would be 2 to the 3/2 power. Now what's another way of referring to that? The square root of 2 cubed, okay? So that would be 2 over the square root of 2 cubed. That would be 2 over the square root of 8, which would be 2 over 2 root 2, right? Which is our good old 1 over root 2. We've had that many times today, haven't we? Okay? What's that? Yes, I believe so. It sort of does. Okay? So 1 over root 2 is your kappa at that place. So what is your radius at that place when x equal 1/2 or t is equal to 1/2, whatever? Radius is 1 over kappa, which would be 1 over root 2, which would be root 2. Got it. Okay. So that's your radius, the radius for that. So we found the radius. That was step 1. Okay. Yeah. Now, following the steps in the book, frankly, I would have probably gone that route earlier, but we can do it now. So what's the normal vector in at t equal 1/2? Remember how we found the normal vector? Say again? Okay, wait. Don't do the last one we did. Do this one. This has nothing to do with sines and cosines. This is a new curve, not a helix. This is a parabola in 2 space. Oh, okay, I'm sorry. Okay. Well, how did you get t? Yeah.
So what is t?
Yeah. Ah, okay. Let's do r prime. R prime. And what is your r prime of t? Or x, or whatever you want to call it. What would that be? 2t. Okay? Magnitude of r prime would be
1 plus 4t squared. Square root of 1 plus
right.
4t squared.
Got it. And your unit tangent vector then at t would be 1 over the square root of 1 plus 4t squared, comma, 2t over the square root of 1 plus 4t squared. Okay? Next, derivative of that. Yeah. This is getting to be somewhat tiresome, isn't it? Okay. Yeah. Let's call this, if you choose, 1 plus 4t squared to the minus 1/2, and this will be 2t times 1 plus 4t squared to the minus 1/2. That will be easier to differentiate a little bit anyway. What would that be?
Negative 1/2 up front. 8t, so that'd be negative 4t up front.
Yeah.
Tangle.
Okay. Oh, wait.
Right?
Yeah, without the 2. You already took care of that, right?
And then in the parentheses, be 1 plus 4t squared to the negative 3/2.
Got it? That was the easy one. Okay. Now we got a product rule. Or you could have done a quotient rule if you had chosen to do it that way. I find product rule, well, whichever.
Product.
Okay.
Easier
Yeah.
than quotient rule. So that would be 2
Okay.
times 1 plus 4t squared to the negative 1/2
Right.
plus 2t times the same as last time, which was negative 4t times 1 plus 4t squared
Okay.
3/2.
Okay. You had a negative.
4t. So
Okay.
if you multiply those two together, you would get negative 8t squared.
Okay. All right. I can't tell who's doing what first, so let me pause here again and,
Doing everything.
yeah. Okay. Okay. The second part would be
Basically, that first
2t.
we came up with
Yeah.
times 2t.
Oh, you mean this over here times 2t. Yeah, that would be okay. So that would be minus 8t squared,
Right.
okay, times 1 plus 4t squared to the minus 3/2. And that would close out that one. Okay. Now, just want to point something out to you, that if you multiply this first term of the second component by 1 plus 4t squared over 1 plus 4t squared, then you get the same denominator, right? So this would be the same as 2 times 1 plus 4t squared over 1 plus 4t squared. I've decided to change the way I was going to write that. Okay. Yep, I'm erasing too much. Okay. If you this is a minus 1/2 over here. If I multiply that numerator and denominator by this, you would get 2 times 1 plus 4t squared times 1 plus 4t squared to the minus 3/2. I know that seems strange to do it that way, but now you got everything over the same denominator. Okay? I don't know if that helps you any or not, but it might. Then this first term could be written as 2 plus 8t squared. Plus, and that's over that denominator, plus minus an 8t squared, and these two go out. So that leaves you with, what I've been trying to do is simplify that. That would be, the first term's fine, minus 4t, 1 plus 4t squared to the minus 3/2. And now the second term, if you do that manipulation to it, you'll find you simply got 2 times 1 plus 4t squared to the minus 3/2. I believe. Okay? Do you buy that? I know it's a lot of messing in a very small space. It doesn't seem like it should come out that simply, but it sure seems like it does. Okay? Now, right.
Okay. Yeah. All right. Then that makes sense. Because this will be done.
Okay. Now again, I don't know if this is helpful or not, but it sure makes it a little simpler to look at. However, everything we're doing is perfectly fine. But they notice here, for a plane curve, there is an easy way to find n without computing t prime. But I thought since we had started t prime, we would. But here's what it is. The tangent vector is r prime of x, which we had already determined to be this. Okay? And we know that a vector that's perpendicular to that, a vector that is, would be this one. And there's several ways you could write it, but minus 2t comma 1. That would be perpendicular to that, wouldn't it? Because when you do the dot product, you get minus 2t plus 2t is 0. Okay, so this obviously would be perpendicular to that. Well then, if this is perpendicular to that, this must be in the direction of the unit normal vector, because this is in the direction of unit tangent vector. Now we're using the fact we're two-dimensional here. All that was okay, but look how messy it got. This is a lot simpler. Okay? Now, what we need to find is the normal for this. This is a vector perpendicular to this, so we're in the right direction of the unit normal vector. We just need to normalize it to get it magnitude of 1, which would be, how would we do that? Magnitude of this thing would be the square root of 4t. Ooh, wait a minute. I'm in the. Yeah, I know. I'm going to erase this down here. Okay. Let's go up higher here. Okay. Okay, never mind. This is the square root of 4t squared plus 1, which is what our denominator was before, isn't it? So what do we have? We'll reverse the order of that so it'll look the same. The unit normal vector would then be this vector here, minus 2t over the square root of 4t squared plus 1, comma 1 over the square root of 4t squared plus 1. Okay? That's where we were heading for with this other stuff, but this is so much easier to do it this way. Now, that's the unit normal vector at any place t. How about when t is equal to 1/2, or x is equal to 1/2? So, unit normal vector at x equal 1/2 or t is equal to 1/2 would then be what? -1 over good old square root of 2 again, comma, okay. Now let's, before we go any further, make sure that's a normal vector, is it? Yeah, of course it is. 1/2 plus 1/2 is 1. Okay. Now, the other thing, are we pointing in the right direction? We're on the 1/2 side, so our normal vector needs to be pointing that way, right? So that would be a negative on the x part and a positive on the y part, sure enough. Good. Makes us feel warm and fuzzy. Okay. They also take out the 1 over root 2 and make it -1, which it doesn't matter. Okay? So there's your unit normal vector. Okay? Now, what would the center be? I'm going to erase a bunch of this, especially stuff we don't need anymore. Okay? We've already done all this, so I'm going to get rid of this and remind ourselves that kappa at 1/2 is 1 over root 2. So I'm going to pull that in. Yeah, we've still got a ways to go before we sleep. Okay. 1 over root 2. Whoops. 1 over root 2. Okay, which also, erase the rest of this, I think we can get by with. Okay, and have the r of 1/2 was root 2. Okay, I don't think we need the unit tangent vector for any other reason. I'm not sure we need, oh, I already erased it. No, I got it. There's a normal vector up there, unit normal vector there. So I think I can erase the rest of this with impunity. But if you were in this morning's Cal 2 class, every time I said that, I'd find something I had just erased that I needed. But I'll have you find it in your notes. That's why I have you in class, okay? To use you, okay? And abuse you, okay? All right.
Living post-it notes.
What's that?
So we're living post-it notes.
Yeah, something like that. Okay. Now, we found the radius. There it was. Didn't know we had lost it, but I'm going to move it over some. Root 2. Okay. We found the unit normal vector. We did that at t is equal to 1/2. Got it. Now we need to find the center Q. Now if you go back to what we did just, our equation 9, just a little bit earlier, we saw that the center Q, the vector OQ, I'm not sure we need this, but I'll write it down because we did, was your initial vector r of t0. Now we haven't actually explicitly stated what that is yet, but we're going to very soon, plus your r times your unit normal vector. Well, what's our r at 1/2? R at 1/2 will be what?
One
1/2,
half.
1/4. Very good. Okay, we got what? That's the vector r, little r. Capital R, radius r, is √2, and there's your normal vector. So what we have here is 1/2, 1/4, plus √2 times that would be what?
Times what? Times the normal.
Yeah, this √2 times that normal vector. This thing
Oh, that would be
times that thing. Oh, yes. What would that be?
-1 and 1.
-1, 1. There it is. And what is the sum of those two then?
-1/2.
-1/2,
And 5/4.
5/4. Okay. Now that would be the vector OQ. Well, we're not really interested in that. We're interested in the point, the center, Q. Well, guess what? The vector OQ, those components will be exactly the values of the coordinates for Q. So that would be that implies that Q then is the point with coordinates -1/2, 5/4. Now, the question, does that seem to make sense? They don't ever quite say the same thing we did there, but they come up with it. Okay. Let's see, what was the question anyway? Parameterize the osculating circle to that at that point. Okay? Now, remember how we parameterize a circle? Okay? To parameter, yeah.
X squared.
Okay. What's that?
Wait, that was something else. Go ahead.
Okay. To remind ourselves, how do we? It's quite a ways back.
It was.
Yeah, it was quite a ways back. I'm almost guessing early in 12, wasn't it? Okay, 11. Okay, I was thinking it seemed like it was 11, but I couldn't even remember we did that this term. 11/9, you say? No, 11/1. Okay, I didn't think 11 had 9. Okay. All right, 11/1. Parameterization of a line, parameterization of a line, parameterization of ellipse.
I think it's the same as an ellipse.
It would be very similar, only there your A's and B's are the same.
Okay. So
Okay?
the cosine sign.
Yeah,
Whatever.
right. That's the circle. But what is your A and the B here? Okay? The A is the center of that circle. AB is the center of the circle, and then the second part of it, the r cosine theta, is then the radius of the circle. You know, that would be what you would do there. Okay. So, to parameterize the circle, goodness, I can't even think how you say this, but this is the last thing, is the r of t, to define that circle, would be locate the center, we've got it, so that would be the, let's call it Q, OQ, plus, okay, then your circle is radius √2, cosine t, √2, sine t. Okay, so this would be negative 1/2 plus root 2 cosine t 5/4 plus root 2 sine t. Okay, the minus 1/2 5/4 moves you where you want, and then the circle is that. So sure enough, they didn't write it that way, but that's how you get it. You write the center, okay, as a vector. They're doing it just like I was indicating there, and then you add to it the circle of radius r. Okay. Now, whew, okay.
Is it the end of the example?
What's that? That was the example. Parameterized osculating circle, there it is. They wrote it as the sum of two vectors with a constant in between. I wrote it as one vector. Either way works fine. Okay, if a curve C lies in a plane, then this plane is the osculating plane. For a general curve in 3 space, the osculating plane varies from point to point. So, whereas osculating circle could be doing this kind of stuff, the plane would then be the plane that contained the oscillating circle. Okay. So to define the osculating circle at a point P on a space curve C, we must first specify the plane in which the circle lies. The osculating plane is the plane through P determined by the unit tangent vector at P and the unit normal vector at P. That then defines the osculating plane. Okay? Excuse me. We assume that T prime is not equal to 0, so the n is defined. Otherwise, unit normal vector is not defined. It's infinite. Intuitively, again, the osculating plane is the plane that most nearly, in quotes, contains the curve C near P, and that's supposedly, oh, I'm sorry. Okay. Jumped a little ahead. Let me do this first. The one we just did was right here. Okay. Here is the point on the curve, y is equal to x squared, at x equal 1/2, y is 1/4. So there's your point P, 1/2, 1/4. Okay? The tangent for that we calculated to be, t, if you want to say it that way, derivative of that would be 2t, so, that would be the direction of the tangent curve, and perpendicular to that, just like we calculated, there's your unit normal vector. Now, this is not, remember the helix whose trace was a circle, unit circle, that always pointed right toward it. This points toward it, but it doesn't reach it because that's not unit length anymore. Okay? In fact, that radius we found to be square root of 2, which is greater than 1. So that's why their scale here is pretty good. And this shows everything we just did. The center was at negative 1/2, 5/4. They didn't show that in the book, but they did show it in the graph. Okay? So that is the point there. And this is pointing toward that from this point. So come up with the parameterization for this circle here. You would include this center and that radius and that normal. You got everything done you needed done. Okay? That was just the figure that showed what we were just doing. All right, here is the one they were talking about. And this gets a bit bizarre, but here we have it. Okay. Here we have a curve, okay? And this is in 3 space. The x-axis is coming out this way, y-axis going that way, z-axis going up. And here is this is the vector, the curve we're talking about, cosine t, sine 2t. So believe it or not, and to me this doesn't look to be true, but if you were to look down the z-axis at this thing, ignoring this component, just look down, this forms a circle of radius, a unit circle. Okay? But what this is doing is going everything else. At time t equals 0, x is 1, y is 0, and z is 0. So you're right there at that point. Okay? And then when t increases, your cosine now is decreasing, so the x is going inward, but the y should be increasing, coming this way, and sine 2t to me looks like it should be increasing too. This looks like it's decreasing. So I have trouble visualizing what they're doing here, okay? But let's just say that they have, okay? So if you're at when t is increasing, cosine is moving in, you start at 1 and go in this way, y is going out this way, and z, why is it not? That looks like it's going down, it should be going up. And it looks like they've got their orientation wrong. I can't justify that. No, actually, to me, it looks like the x-axis should be coming this way. And this should be our starting point right here. I think they've got the x-axis rotated wrong. Okay, over here. So this is 1 on x, 0 on y, and 0 on z, wherever that would be here. And then you go up here and down here. That makes sense. That would make perfect sense. Okay? Okay, and then you go this and this and this. Yeah. I think the x-axis is just pointed wrong, but I don't know why they have it that way, but it is. Okay, now, this is example 8. So maybe I've jumped ahead some. No, I still don't see. Okay. But to define the osculating plane, here's figure 16. Notice that because it contains the vector T, P, NP, the vector BP is normal to that plane, which we haven't even messed with that yet. The osculating circle is a circle on the osculating plane through P at the of radius R, yeah, we know that, whose center is located in the normal direction NP from P. So all that remains true. So all they're doing is here, osculating circle at T equal pi force. Okay? That would be, if this is 0 and this is pi, basically, the pi halves there, pi force would be exactly along the bisection, and then you go up and that's what we got. So there's the place where your osculating circle is one of the tightest you could have here, okay? Because that's the place. Right here it would be somewhere, there it would be somewhere, here it would be somewhere. So that's one of the smallest osculating circles. How did they get the curvature K equal 4.12 here? Well, what you would have to do is, now you're in 3 dimensions, there aren't any cheap fixes here. How are we doing on time?
You got about 7 or 8 minutes.
7 or 8 minutes.
Test back. Can you see my test back real quick?
Sure.
Just one little thing.
Oops. I just don't want to give you David Brown's test. Okay, there you go. Okay. So an easy way to do this in a very short amount of time. We don't have any shortcuts here, so basically you have to go through the curvature. You're not in 2 space anymore, you're in 3 space. Okay. So your best one is Theorem 1 on page 713. That's your equation 3. Let's see if we can do that quickly. Okay. Your curvature here, and of course, going to shrink this. The curvature as a function of t is given in, got it? All right. How would we proceed? You see the formula there? What 2 things do we need to calculate? Our prime of t would be what? That's a vector. Help me, help me. Page, near 713, it's Theorem 1 in section 13.4. You see it? You're going to need R prime. So what's your R prime? Here's your R. R is cosine t, sine 2t. What's your R prime? Derivative of cosine. Negative sine t. Derivative of sine. Cosine t. Derivative of sine 2t. A little louder? Times 2, right? 2 cosine 2t. You buy that? Okay. Next thing you knew is R double prime of t. What would that be? Negative cosine t. Negative sine t. Negative 4 sine 2t. Got it? Now that you have that, your kappa is the magnitude of your R prime of t cross your R double prime of t divided by, that's pretty ugly, the R prime of t, magnitude of R prime of t to the 3 halves power. Okay, that's one of those weird third power. Okay, when you take the square root, that makes it 3 halves power, but we won't mess with that right now. Okay, so we've got to cross those 2. Okay, can you cross them easily? Again, I, J, K, I, J. Go on and do them out since the camera's not here. Minus sine t, cosine t, whoops, I didn't leave enough room. Forget this, okay. Let me write out what they are and then put my J's and K's in, okay. All right. It's minus sine t, cosine t, 2 cosine 2t, minus sine t, cosine t. Now I'll put my I, J, K, I, J. Okay? And then the next one is minus cosine t, minus sine t, minus 4 sine 2t, minus cosine t, minus sine t. Okay, now do your cross, and what do you get? Minus 4 cosine t sine 2t, right? Minus, which is then going to turn out to be a plus, 2 sine t cosine 2t. That's the I component. Okay? The j component, okay, j component will be minus 2 cosine 2t's cosine t. Okay. Minus 2 cosine t cosine 2t. Plus, no, minus, because you got a minus times a plus is a minus, 4 sine t sine 2t. That's your j. And your k is these. That would be sine squared t plus cosine squared t, which I can do. That's 1. So that's k. 1k. Okay. It would be okay now to plug in t equal pi fourths. Okay? We're probably running out of time. Huh? Past time. So if you plug in pi fourths there, okay, for this one, you can work out what all those are. You know what cosine pi fourths is, sine of pi halves, sine of pi fourths. You can plug in all those numbers, and this is just 1 down here. Okay? And when you do that, and then take the square root and do all the things you need there, you can do it. The r prime of t, remember, here it is. You take the square root of all that and cube it, okay? So you have to do that and do your magnitudes. And supposedly you'll get curvature kappa to be 4.12 for this one, and then you do all the same thing for pi eighths, and you get a kappa of 0.64. Much larger circle at pi eighths, which means a much smaller curvature. You tell me, do we start there next time or move on from there? I guess we need to finish it. So we will continue with B here. Boy, this took longer than I intended. We're somewhere in example 8. Okay, we'll pick up from there. Homework exercises here you can do. I'm trying to find my marker page. Oh, here it is. Yeah. We almost finished the section. We are right at the end. Any of the odds 1 through 5, either 5 or 7 or 9 or both, either 11 or 13 or both, either 15 or 17 or both. Do 19, well, I'll let you choose, any of the odds 19 through 27, either 29 or 32 or both, 33, you might need a computer to do 35. See if what you can do on it. Any of the odds 33 through 39, 41 or 43 or both. Wow. 45, do 45, and then, let's see, 47 and or 49. No, any of the odds 47 to 51. 53, any of the odds 53 through 57. And any of the odds 59 through 65. stop there. We'll pick up any of the rest of those later. Good deal. Sorry. Man. Complicated.